Rarely, if ever, do we get to work with hydronic systems as simple as the schematics we have been looking at. There's usually more than one load, or coil, that a given system is serving. And there are different piping configurations that we could use to bring heat to or from all those various coils being served by the hydronic system. The first such piping configuration is that of the series loop. Here we have the hot water brought to the first load. It gives off some heat, and then the water leaving that first load goes directly into the second load. This occurs again and again for all the loads being served by the system. There lays two issues here. First off, the temperature of the water is constantly decreasing. Thus, if all the coils were the same physical size, a lot more heat would be given off in the first coil since its entering temperature is much higher. As you move further and further downstream, the entering temperature to each coil is less and less, and the potential to give off heat is constantly being diminished. The second issue is that of control. What if the space being served by the second load is getting overheated? They can't just shut off the heat being provided to them without shutting down the flow of heat to everyone else. This piping configuration is never installed anymore, but some of the older buildings on your base may still have them. One of the chapels at my first duty station had this type of piping configuration, and it created some issues for us. The only advantage to such a system is the decreased installation costs, since you get by with a lot less piping. There are several variations of this series loop that we will not go into in this lecture, but hopefully by the end of this lesson, you'll be able to look at such configurations and be able to determine the inherent issues that they present. We can also have a parallel loop piping configuration. In this configuration, there is a dedicated supply pipe and a dedicated return pipe. Each load pulls directly from the supply pipe, which means each coil is provided the same entering water temperature, and thus each coil has the same potential to expel heat from the hot water loop. There are two styles of parallel loop piping configurations. The first one shown here is called direct return, because as soon as the water goes through the coil, it directly starts its path back towards the boiler. There remains an issue here. Say each coil is sized for 10 GPM of flow. That means on the coldest day of the year, each coil would be calling for 10 GPM of flow. Though there are control valves installed at each coil, we would want them operating in a fully open configuration since the system is operating at design conditions. Even though they all want 10 GPM of flow, with all the control valves wide open, more flow is going to travel through the path of least resistance. That path would be through the first coil. So to prevent load 1 from getting more than its fair share of water flow, we have to install what is called a balancing valve. This is just a valve, which we close part way to create more resistance to flow through that particular path. Now, more flow will want to go to the coils located further from the pump. To prevent coil 2 from getting more than its fair share of flow, we would also need to put a balancing valve there. It just probably won't be quite as closed as the balancing valve located at coil 1. So theoretically, we could install these balancing valves and adjust them until we got the correct amount of flow, 10 GPM, through each coil. But if coil 3 was excessively far away, this process could become very difficult and time-consuming. So, we often see another style of the parallel loop piping configuration installed. It is called the reverse return configuration. In this configuration, the flow leaving load 1 does not directly head back to the pump. Instead, it goes to pick up the flow coming out of the other coils before it heads back to the pump. In this configuration, it is pretty hard to determine the path of least resistance. For the flow going through load 1, it will have to travel through roughly the same amount of piping that the water flowing through load 3 would have to follow. Thus, the layout is inherently more balanced to begin with. Now, we are still going to need to install balancing valves on all these coils and go through that process of adjusting them until the flow rates each of these coils are designed to be pulling are realized. But with reverse return, the process will be a lot less painful and a lot less time consuming. Now, this process of adjusting all the balancing valves to ensure the right amount of flow is getting to each coil is literally called the balancing process. It is performed by a testing, adjusting, and balancing, or TAB subcontractor after the system is installed, but before the occupants move into the space the system serves. It is often reaccomplished at various times throughout the life of a building, especially when the function of the building has changed or a portion of the HVAC system has been renovated. The balancing process includes the adjusting of all the balancing valves in the hydronic systems, but it also includes a similar procedure to be done on the ducted air systems as well. We will talk a bit more about that in a few lessons from now. The balancing process is done by running the pump at full speed and keeping all the various control valves wide open. It is an iterative process because if you adjust the position of a balancing valve at load 1, it changes the flow through all other coils. So the tab team might have to adjust the balancing valve at load 1, then at load 2, then at 3, and then redo the whole sequence several times until they get all the flows to within the specified tolerance. For example, plus or minus 5% of design flow. But what is each respective coil's design flow? We can find that by looking in the appropriate schedule on the mechanical schedule sheet of a drawing set. If we were looking for a coil located in an air handling unit, we would probably go to the air handling unit schedule and such design flows would be labeled there. If a larger pump than is needed is installed in the system, the balancing valves may have to be closed quite a bit before they could achieve such tolerances. So often, another balancing valve is installed on the discharge of the pump, so we don't have to close the balancing valves located at the coil quite as much. Balancing valves located on the discharge of the pump are often called throttling valves. If you have ever heard of a triple duty valve, that is a valve located on the discharge of the pump which serves three purposes. First, it can be adjusted during the balancing process. Thus, it is a throttling valve. Second, if maintenance needs to be accomplished on the pump, the triple duty valve can serve as an isolation valve. And lastly, the triple duty valve can serve as a check valve to ensure that at no time water is allowed to flow backwards through the pump. So the balancing process is an iterative process of adjusting the balancing valves at the coil as well as the throttling valve on the discharge of the pump. Once the tab subcontractor completes this process, all such valves are not adjusted anymore, unless if there is some renovation to part of the system that would warrant a rebalancing effort. The building next door to the Civil Engineer School was rebalanced during the summer of 2016. Captain Dill and I had the opportunity to follow these guys around and annoy them with our very academic questions. Here's a video of one of Seymour's best, Mr. Jeffrey Fogarty, trying to determine the flow rate entering a chilled water coil in a rooftop unit.
What is wrong with these things?
As I said, what he's trying to do here is to determine the flow rate entering a chilled water coil in a rooftop unit. He is doing this by looking at the position of the balancing valve, as well as taking the pressure drop across that valve. Those two such values can be used in conjunction with the balancing valve manufacturer's performance data table to determine the flow rate of water flowing through it. Now, the chart just shown has the term circuit setter in the title. This may be a term you have heard before. Often people refer to both balancing valves located at the coils as well as throttling valves located at the discharge of the pump as circuit setters. But circuit setter is a brand name for a series of balancing valves manufactured by Bell & Gossett. It is probably the most commonly used balancing valve, but it is not the only one out there. So the generic use of circuit setter is like someone calling a tissue a Kleenex. Technically, not all tissues are Kleenex, and technically, not all balancing valves are circuit setters. So why are we describing the balancing process in a controls course? Well, if you don't have a properly balanced system, the chance of being able to control it properly is slim to none. The balancing process is done with the control valves wide open. This ensures that on the coldest day of the year, the control valve can fully open and the correct amount of flow will be provided. All other times of the year, the control valve will be positioned somewhere less than fully open, depending on the heating requirements of the building. If the system was not balanced correctly and excessive amounts of water want to flow through a particular coil, one or maybe two things will happen. First, the control valve is going to try to compensate by always being partially closed. This reduces its operating range and thus its ability to control the amount of flow being provided to that coil. Second, if the system was extremely unbalanced, overheating may occur in the space served by the coil when the control valve is barely cracked open. To tie that back to some control theory we have already discussed, we would say that particular coil and control valve assembly would have excessive system gain. So to sum it up, balancing and controls go hand in hand. It is extremely difficult to control an improperly balanced system. Thus, we always require balancing to be performed. That balancing process is time intensive and expensive, so there are folks who are constantly researching ways to ease the burden. A great read, that is also a very difficult read, entitled Balancing Variable Flow Hydronic Systems, has been made available to you if you are interested in digging further into this topic. So it is easy to see that a parallel loop reverse return configuration has many benefits, especially when it comes to the balancing process. But these types of piping configurations also require a lot more pipe, which is an added cost during construction. Therefore, you will often see, even in new construction, hydronic systems which exhibit a direct return piping configuration in some portions of the system, while other portions of the same system exhibit a reverse return configuration. The last thing we need to discuss during this hydronic systems overview lesson would be that of the different pumping configurations. Thus far, in the simple schematics we have been showing in this lesson, each hydronic system only had one pump. That is not always the case in real systems. So let's look at some ways multiple pumps can be arranged and define some terms. Taking that initial schematic of a hot water system I had before, if we added another pump to it, we could do so in one of two ways. First off, we could add them in series with each other. I have never encountered an HVAC hydronic system which actually utilizes such an arrangement. Issues occur if one pump is sized for higher flow rate than the other, in which case the forcing of the fluid through the smaller pump quicker than it can handle it can be very damaging to that pump. Cavitation can occur in the smaller pump, and there may be actually a chance to have a pressure drop across the smaller pump, not the intended pressure increase. Nevertheless, when pumps are used in series, the effective pump curve with the system curve overlaid on it looks like this. It is important to note that when pumping in series, each pump sees the same flow rate, but they both add pressure into the system. More commonly, we see a second pump piped in parallel. This is often done where both pumps are sized to push the entire system's flow requirements. They are fully redundant and never operate at the same time. Often, the control sequence would be to operate one pump for, say, 100 hours, and then the next pump for 100 hours, equally distributing the wear and tear on the pumps. If you are going to do this type of schedule, however, it is best to stagger the total operating hours between the pumps by a few thousand hours. Otherwise, you might have both pumps crap out on you at the exact same time, which would completely negate this idea of full redundancy. There are also times when both pumps operate together when the hydronic system is calling for higher flows. The resultant pump curves with the system curve overlaid looks like this. It is important to note that when pumping in parallel, each pump provides the same pressure increase to the system, but their flows are now additive. All of the system configurations thus far shown today have been primary systems. In a primary system, all of the flow that goes through what is called the primary equipment also goes through the respective loads. Primary equipment would be the equipment that is generating heat, for example the boiler, or those that are extracting heat from the hydronic system. That would be the chiller. It should be easy to see that if 100 GPM is flowing through the boiler here, then 100 GPM must be going out to the loads it is serving. There is another pumping configuration that is very common where this is not necessarily the case. It is called the primary-secondary system, or often called compound pumping. It looks like this. You have two separate piping loops, which are connected by a common pipe. This common pipe is often called the decoupling line or the neutral bridge. Flow can go either direction through this common pipe, or not flow through it at all. Let's walk through a couple examples. First off, the pumps which serve the primary loop, that is the loop with the chiller or the boiler, are called the primary pumps. The secondary pumps are those located on the secondary loop, which sends water to the various loads. The reason for separating the hydronic system into two loops is to allow for variable speed pumping in the secondary loop, which we will show later on how that saves us a lot of energy, all while maintaining constant flow through the primary equipment. Maintaining constant flow through the primary equipment is a practice used to protect that primary equipment, and that concept will be further explained later in this course. If one of the primary pumps is operating at 100 GPM, and there is not that much load on the system and the secondary pumps are operating at a reduced speed and only pushing 75 GPM, then 25 GPM will be flowing downward in the common pipe as shown. If the building load increases and the secondary pumps start speeding up, there will come a time when all of the flow coming off of the chillers will be sent to the coils. In this instance, there will be no flow going through the common pipe. Say the coils keep calling for more and more flow. Then there may be an instance when the flow is going upwards through the common pipe. That would be a good indication for an additional chiller and corresponding primary pump to turn on and make additional chilled water available to the secondary pumps, which in turn they can send to the coils. There are different ways in which these chillers are staged on, and such control sequences will be discussed at length during the primary equipment staging lesson of this module, as well as during the low delta T syndrome lesson of module 3. So that is the primary-secondary pumping configuration. It is very common these days, but does have some inherent downfalls which we will discuss later on in the course. A big takeaway here is that the primary pumps are to be constant speed, while the secondary pumps are to be variable speed. Constant speed primary pumps maintain a constant flow through the primary equipment. The reasons why we do this will be discussed later on in the course. Variable speed secondary pumps allow us to change the flow rate going to the coils depending on the cooling requirements in this example. Reducing flow at lower loads helps save on pumping energy that is being consumed. That is it. We got through another lesson. We hope you feel a bit more comfortable with all the major components of hydronic systems. We also hope you have a better understanding that having a quality hydronic system layout and design can make controlling that system much easier. There are a lot of things in hydronic systems we haven't got to yet, like how does the boiler and chiller modulate on and off to keep the required supply temperature? Or how does the coil determine how much flow it wants sent through it? Or how do we control multiple pumps in parallel? All of these control sequences, which are part of the hydronic system, will be talked about in the lessons ahead. HVAC controls is a very difficult topic. It requires a very thorough understanding of the system you're trying to control. That is why we have to take this one step at a time. Again, the lesson objective for this lesson was for students to comprehend the functions of the major components of hydronic systems, as well as understand the benefits and limitations of various piping and pumping configurations. The corresponding samples of behavior were: describe the best location for an air separator in a hydronic system, state the general relationship between pressure drop and flow through a hydronic system, differentiate between system and pump curves, distinguish between different piping configurations, describe the implications an unbalanced hydronic system will have on the controllability of such a system, and distinguish between different pumping configurations.